Yeah, so let us get started with the things. So first let us try to understand how does a distributed winding produce a sinusoidal uh, B in the ear gap, as we have seen in the earlier case. Like in this case, we are having distributed winding and we are able to produce some sinusoidal B distribution. So what does it mean? If we pass on a ear gap through this air gap circle, then we see if we start from say theta equal to 0 and traverse throughout that, we are able to see that we are getting some B distribution which has some fundamental sinusoidal component, and along with that it has certain other harmonics also. So we'll probably take this example and uh, see quickly how do we get how is that how can we basically analyze this type of structure to see that yeah, the B distribution is sinusoidal. So for that, let us, so the current directions are already are clear here. So if the R phase current IR is positive, then these ones will be cross and these ones will be dot. If I similarly IY is positive, then this upper side will be cross, this lower side will be dot. Then even
Sir, sorry to interrupt you. I am
yeah,
unable to see the your screen.
I think it is visible. The same screen is there before me also, so it is visible. Just check your internet connection once. Yeah. So the IB current, uh, if IB is positive, then these ones will be cross and these ones will be dot. So let us take one instant. First let us understand what happens at an instant. So omega t equal to, let us say for simplicity of the values, let us say 90 degree, and say if all the currents are 10 sine omega t and phase shifted versions of that, then IR will be 10 ampere, IY will be minus 5 ampere, and IB will be minus 5 ampere. Let us consider that in every slot there are 10 conductors, 10 conductors per slot. So for this case, if it is a two pole machine, so suppose we have to know that what is it wound for. It is, if it is a two pole machine and we know what is the number of slots, it is 24 slots. So we have to construct some loop which is having this slot per pole, basically 24 by 2 12, which covers 12 uh, slots. That basically means 180 degree. Let us start from 0 degree. So this is our 0 degree. Let us construct one amperian loop. So here it completes, and this is how one loop can be constructed. The direction can be anything, clockwise, anti-clockwise, so we have to fix that. Now it is possible for us to write Ampere's circuital law in this loop. So basically H dot dl equal to the enclosed current, right? This loop can be divided into two portions. One, the small air gap portion, that is there in this portion and in this portion. So basically this can be divided into two portions, H dot dl in air plus H dot dl in iron, that is the I enclosed. Now if we consider the mu r value, the relative permeability of iron, to be quite big, then the H in iron will be negligible. All the significant H will be there in the air gap only. So this second portion can be approximated to 0. Now along this air gap, this H is direction is radial, and the dl, because that is dl on the loop, so that is also radial. So H and dl vector both are collinear, so H dot dl basically becomes H dl, and that is true here. That is equal to I enclosed. Now basically there are two parts, one this portion, another this portion. So again H can be assumed to be almost uniform in this small air gap. So H as a constant will come out of the integration, and we have to just integrate over the for DL over the air paths, and this is I enclosed. And this is basically H into 2G, because G in this portion and another G in this portion, that is equal to I enclosed. So H equal to I enclosed by 2G, right? So that is what we get. Now if we the takeaway from here is H is basically or basically H into 2G, 2GH is basically I enclosed. So that is the key thing here. I'll I'll remove the other things. Now we have to look at what is the current enclosed by this loop. Now IR, this is I'll write with black. So IR is positive, so these signs will be retained. So this has 10 ampere, this has 10 ampere. IB is negative, so it will become cross, dot will become cross, and it is 5 ampere, 5 ampere, 5 ampere, 5 ampere. And IY, that is also negative, so this will become this one will get flipped, this one will become dot. So you will have um, 5 5 5 5, and again red conductors, that is basically dot. So the same thing will be retained, because IR is positive, so it is 10 and 10. Now if we consider cross polarity to be positive, then how much do we have? 10 plus 10, 20. Then again 4 cross, that is like a more 20. Then this 4 cross and this 4 dots will cancel each other. So whatever 20 this form, this 20 will be neutralized by this 20, and again you have 10 and 10, which are basically dot. So my plus 20 for these R conductors and minus 20 for these R conductors on the opposite side, and these blue conductors basically cancel each other, so effectively you have 0. So you have 0 H in this region for this loop. So drop in H will be so H at this point will be 0, and similarly at this point also it will be 0. This is clear. Now we have to move this loop to the next point. So we'll have to move this loop no, it is getting changed. So we'll have to move the loop. So earlier we started the loop from here. Then if I go to the next slot and continue this, then if the same calculation is done, then you will be able to see still these blue conductors for the same currents, for the same instant, omega t equal to 90 degrees, same currents. So this blue cross and so basically this blue cross and yellow dot, they will cancel each other. One R cross will be cancelled by one R dot, so effectively this will get added and this will get added. So we'll have some addition. So whatever, so this is 20 and this is 20, this is 10 and this is 10. So we have 20 as the enclosed current, and if 10 is the number of conductors per slot, then multiplied by 10, that is 200 ampere conductor is getting enclosed. Now this total H will be dropped along the two gaps. So half will get dropped here in this slot and another half will get dropped in this slot. So in this angular position you will have 100 ampere conductor, and in this zone you will have, in this air gap position you will have another 100 ampere conductor drop. That is the mmf drop. From mmf, if you want to calculate h, then you have to divide it by the length, that is g. Now you have to we have to be careful about the sign. So if one case it is positive, another case it will have to be negative because of the direction. So if we consider h to be positive, if it is outward, then you can see in this portion loop direction is radially outward, then in this region loop direction is radially inward. So for one case, if we consider so h magnitudes are same for both cases. So if one case it is radially outward, and if we assign positive sign to it, then other side we have to assign negative sign towards it to it. So this is why in this theta region, theta location, and around that on this tooth we'll have 100 ampere turns positive, say 100 ampere turns positive here, 100 ampere turns negative here. Similarly, if we traverse this loop by taking traverse this circumference by taking different loops, it will be possible to be shown that the mmf distribution that we have in the air gap, that is a stepped thing which has a significantly high sinusoidal component, and the same thing h divided by g, that is the h distribution along the circumference, that is also same. And so we have if we get b, the flux density, that will also have a similar thing. Now b, what is the difference? Why are we looking why are we seeing uh, these notches? So notches are coming in every slot opening portion. So you can see that air gap is uniform when there is a cylindrical rotor under the tooth. Under the tooth, the air gap is uniform. Under the tooth, the air gap is uniform, but in the slot opening regions, the slot opening regions, the air gap is higher. That is why the effective reluctance in those regions is also higher, which is uh, resulting in the notches, the downward notches in the b distribution that we saw earlier. So yeah, this mathematics if we do, then we will basically have this type of uh, mmf distribution. So some mmf, then there will be a stepped change, then there will be another stepped. So similar, if I whatever I showed, if we complete the whole thing, then we will get mmf distribution in the air gap like this, stepped like this. And yeah, this will have a significant uh, fundamental component. And what we have what we have so this was the loop that we had taken. So this was the second loop where we have some positive thing here and negative thing here, and the initial loop was at 0 degree and 180 degree where everything was 0. So is it clear
Thank you,
how
Samrat.
we are getting? Yeah, okay. So so after that we have
One more question I have. So last time you
yes,
mentioned that we need this Fs equal to Fr or the
yeah,
state
that
field
I'll
rotor
come.
field. Yeah.
Yes, I'll come to it.
Okay.
So then we have understood this 2 pole and 4 pole. Next we started with this rotor realization of the rotor magnetic field. So we looked at the possibilities. The first thing we saw was what happens if we make some winding in the rotor, and pass some DC current through it. Then if we do the run the simulation, we'll get flux line distribution like this, where this is the magnetic axis, this is the magnetic field axis. Now if we make the rotor to rotate, then the magnetic field axis will also rotate, as can be seen in this animation. So we are able to produce a rotating magnetic field by putting some conductors in the on the rotor and passing a DC current through it. So that is the first thing. Now we understood that we can either produce either have a cylindrical rotor and make winding like this, and realize the rotor magnet, electromagnet basically, or we can have salient poles like this, whatever I discussed earlier. So the question is, how can we so what is the difference, is there any difference between these two? So in terms of torque production, principle of torque production, that is same, but there is if you try to do the analysis, I'll briefly show you. So in this case, where are our R phase conductors? Our R phase conductors are here, cross 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 cross, and here dot 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 dot. So this is our R phase conductors. We are talking about one phase only. So the R phase magnetic field axis is actually vertical. This is vertical. This is the R phase axis. Now you see the R phase coil inductance actually depends on the rotor position. Now if I run the animation, the rotor rotates. You can see when the rotor is vertical, then the axis is having maximum or minimum reluctance path or maximum permeance path. So the inductance will be maximum. But if the rotor rotates and comes somewhere like this, you can see that the slot comes in the gap portion along the axis. So the reluctance is maximum, so inductance of the R phase coil is minimum. So the all three phase inductances are actually dependent on the rotor position if we have a salient pole synchronous machine. So the analysis that we do will be quite different for the two cases, the salient pole synchronous machine and the cylindrical rotor synchronous machine. And there will be additional torque for saliency also, the salient pole synchronous machine. Is it clear?
Thank you, Samrat.
Okay, so we'll then move to the next part. Okay, so one more point was there. So the last day I discussed that we can, and then I made a point that yeah, if permanent magnets are energy dense, because permanent magnets are energy dense, the size of the permanent magnet synchronous machine can be quite low compared to traditional this wound field synchronous machine. So can there be a uh, quantitative thing like this? So actually if we try to compare the energy densities of magnets and field winding, so some iron core coil with some field winding, then the energy densities that are possible, they are actually quite different. So magnet PMSM or permanent magnets, they have energy density as high as, say, uh, forgot the numbers, but they are at least some 8 to 10 times compared to one electromagnet. And what do we mean by energy density of permanent magnets? So what do we mean by permanent magnets? So we have BH characteristic of any magnet. So if we have no H, that is no magnetic field intensity input to the magnet, then there will be some remnant flux density, that is Br. So this is flux density and this is H. So if H is 0, then there will be some remnant flux density. And if B permanent magnet. And another thing is, even if we apply some negative H towards it, then it will reduce, the B will reduce, but it should not demagnetize very quickly. So another important thing is coercivity, that is Hc. What negative field, at what negative field the remnant flux density basically goes to zero, or the permanent magnet becomes magnetic property goes away. So this characteristic in the second quadrant is known as the demagnetization characteristic of for permanent magnets. So I'll just give a brief example. So say we have a permanent magnet NS. Now say it is the source of magnetic energy, so it is supposed to give magnetic energy in this type of a iron core like this. Now you can see that this will drive flux into this core. So if we write magnetic circuit equation, then this can be decomposed into two portions. One, uh, mag this magnet flux density and magnet H, plus if we write that equation, this KVL equation for magnetic circuit, HM into H B other portion, basically that is significantly the gap portion, because iron we can assume that it is negligible. So basically B gap into H gap, that will be equal to 0, because there is no other MMF source other than this permanent magnet. So H magnet that will be visible to it will be negative of Bg divided by Bm into Hg. So if we simply keep a permanent magnet in some portion, then naturally some negative field, because this sign is negative, so some negative flux field intensity will get applied to it, and it will the operating point will shift in the second quadrant. Say it will come somewhere here based on the H value. And how will this point be decided? That will be this characteristic known as this so for the other circuit, whatever, if this is simply written, then there will be some line like this, which will be of course dependent on the air gap and other things. So it will be somewhere here. So this will be the operating point. So you can see that it has reduced. So the so on this demagnetization curve, if we calculate B into H on all points, so B into H represents the maximum energy that the permanent magnet can transfer to an external magnetic circuit. So if for any permanent magnet data sheet, this number will be available, so some kilojoule per meter cube, that type of number. So that number for the magnets that we have, like neodymium magnets or samarium magnets, those are quite high. But if we try to realize the same energy or same energy density, suppose we are talking about wound field. If we That means we have some coil and we have some air gap. Now the energy density that the coil can produce, that is basically the energy density W is 1 by 2 mu naught into B square. So for a given air gap, what is the flux density that it can create? So this number gives the energy density produced by for an electromagnet. Now you can understand, suppose it wants to create the same B field. Now you will require a lot of turns, lot of current and currents will also have some losses, so thermal things have to be taken care of. All those practical aspects will come up, and that is why even the size of the coil, because you have to house the coil, then cooling arrangement has to be done, other things. That is why for getting the same energy, permanent magnet, this number is at least 8 to 10 times that we can get the energy density for a coil. So but the size is not actually 8 to 10 times lower, because there are practical limitations in the flux density values. So typically they say that compared to permanent magnet, compared to wound field machines, the B that you can go So in wound field machine, typically the average flux density you can go is typically 0.8 Tesla to 0.9 Tesla, but for permanent magnet machine you can go as high as 0.2 Tesla also. So some 20 to 30% increase in that. And additionally, because you do not have any field winding, so you do not have any losses in the on the rotor, so you can increase the ampere, increase the current that you can pass through your stator itself for the same geometry. So there also some 20 to 30% increase can be there. So overall induction machine or the cylindrical pole synchronous machine, compared to that, PMSMs can be roughly 60 to 60% less volume for the same power rating. Rough numbers. Yeah. So let us get into the second case, that is the case for asynchronous machine. So we started by putting some AC current into the rotor. So the winding we know how to make, and if we pass the current, say 10 hertz current, if we pass, so what is the 10 hertz is the current flowing into the rotor. So 10 hertz corresponds to 600 rpm. So if we run the animation, then it is possible to see that with respect to rotor, because rotor is also stationary in this case, the field is rotating in the anti-clockwise direction and it is running at 600 rpm, right? So the speed of the rotor magnetic field omega fr with respect to with respect to rotor is basically 600 rpm. Now if we run the rotor, at 2400 rpm in the anti-clockwise direction itself, now we will see that because rotor itself, omega rotor, that itself is 2400 rpm in the anti-clockwise direction. Now the rotor field that moves with respect to rotor at 600 rpm. So the speed of the omega fr with respect to stator, which is stationary, or ourselves, we are also stationary. So applying relative speed principles, that will be 2400, because both are in the same direction, plus 600, that is 3000 rpm. So we saw that if we pass some current, say 10 hertz current, which corresponds to anti-clockwise direction of rotation in the of the rotor by 600 rpm, and if we run the rotor also at 2400 rpm, then relative speed of the stator of the rotor magnetic field with respect to stator or any stationary observer, that will become 2400 plus 600, that is 3000 rpm, which is eventually same as the speed of the stator magnetic field with respect to stationary observer, of course, with respect to stator, as seen by stator. And that is why we have two magnetic fields which are rotating with respect to a stationary observer at the same speed. So that means, and we discussed briefly the last class that so basically we have one stator magnetic field that is rotating at omega stator magnetic field, say omega s, let us say, and the rotor magnetic field fr, this was fs, this is also rotating at omega s with respect to a stationary observer. This has two components. One is the speed of the rotor itself, and next is the speed of the rotor magnetic field with respect to rotor, which is basically often termed as omega slip. So this omega s, both these omega s are equal. So this is their relative position in time 1, the time equal to t1. Now at time equal to t2, the relative position may change time equal to t2, this fs may eventually go and come there, and fr may come there, but the angle, because both are running at the same speed, so the displacement between the two will remain the same with time. So uh, that satisfies our criteria for continuous torque production, that is we need two magnetic fields and there should be some, their relative speed with respect to each other has to be 0, so that there is some angular displacement. Now also we discussed that how can we understand that it is motoring action or generating action. Suppose the rotor is rotating in the anticlockwise direction, in the anticlockwise direction. Now for rotor, as it rotates, it sees the stator magnetic field ahead and rotor magnetic field behind. That means stator magnetic field, for the drawing that I have drawn, for the arrows that I have indicated, stator magnetic field and rotor magnetic field. So for this case, the rotor sees stator magnetic field ahead and rotor magnetic field behind with respect to the stator magnetic field. That means Fs is leading, Fs leads Fr. So when stator, so basically power transfer happens from the leading side to the lagging side. So in this case, it will happen from the stator to rotor. So that means it is a motoring action. But had it been generating, then Fr, this Fr would not be here. Fr would not be here, but Fr would basically be ahead of Fs for the same direction of rotation. So in this case, as the rotor rotates, as you can see, it sees that the rotor magnetic field is actually ahead of the stator magnetic field. So Fr leads Fs. So energy transfer will happen from the leading thing to the lagging one. So that means it is energy transfer is happening from the rotating rotor thing to the stator, that is generating action is happening. So these things we had discussed the last class, and we have just recapitulated those things. Now we'll ask a question: is it actually important, or is it actually necessary for us to give excitation in the rotors, or that can happen automatically also? So to understand that, we need to understand what do we mean by flux linkage for a conductor or turn. So say if we have a turn like this, if we have a turn like this, and if we have some magnetic field, if we have some magnetic field in this region, then magnetic field is basically the flux linkage. The flux linkage psi for this coil is defined as surface integration of B dot ds, where you have this area of this area, and you take some infinitesimal area in this region ds, and you take the surface integration of that, and you get, this is how uh, you get the flux linking that one turn. Now for a conductor, it is suppose I'll just draw it like this. Suppose we have a conductor, say dot, then any flux, and there is a, say, some flux line, there is a some field. I am drawing some field line. Suppose some conductor is here, say dot, and because of this there is some field created, right? Now if I place some other conductor in this region, right? So in this region, if I place it, then these flux lines will also enclose, some of these flux lines may also enclose this conductor. So we can simply find out what is the flux, or we can again take a integration, surface integration of B, and find out what is the flux what is the enclosed flux uh, by this by this conductor, and that becomes the flux linkage for this green conductor that I have indicated. So turn, in terms of turn, it is quite simple to understand. We have defined area, and we can take a b dot ds over it. In terms of, for conductor, we have to see what is the what are the flux lines which is enclosing that turn, enclosing that conductor. So that becomes the flux linkage for that conductor, for that conductor. So we'll basically try understanding flux linkage for the three coils that you have put on the rotor. So for simplicity, although we have many coils, we have just indicate I have just indicated a few of them. So this is one coil. So the relative, so the direction is such that this is cross and this is dot. This only indicates the direction of the direction of the winding. This does not indicate in any current. So if we have a coil like this, we have a coil wound like this. If the current is positive, then it will be cross here and it will be dot here. That is the meaning of putting cross and dot here. Similarly, we have two other coils. One, say here it is cross, here it is dot, and again here it is dot and here it is cross. So we have three phase shifted coils. So the direction is such that, so if it is cross, if it is dot, then the axis is basically like this. So this is the red one, red phase axis. Now the yellow phase axis will be like this. This is the yellow phase axis, and this is the blue phase axis. This is the blue phase axis. Okay, I have drawn with respect to stator. So this is the blue phase axis. These are the conductors dot and cross, right? This is the blue phase axis. Now we have put three turns equally shifted from each other, that is whose axes are shifted by 120 degree in space on the rotor. Now we are of these by these coils. If we excite the stator, we excite only the stator, there is no excitation to the rotor given. Okay, so we give some excitation current, three phase current excitation to the stator winding. So we know that we have a rotating magnetic field whose axis is like this at omega t equal to 0, that is 0 time. This is like this. So that means flux, this is indication of the direction of the flux line. So flux lines are going radially outward here in the right hand side direction, that is they are entering the stator, that is why it is south pole here, and this side it is north pole here, right? So this is the magnetic field axis at omega t equal to 0 degree. Now if I run it, now you can see that because we are giving 50 hertz of current excitation, 50 hertz sinusoid of current excitation, so the magnetic field is rotating at 3000 rpm. So it is rotating at 3000 rpm. Now the rotor remains stationary. So what happens because of that? So can we see that? So if we'll understand them point by point, what happens in at different instants. But if we just see the plot, so the flux linkage of the three phases, three rotor phases. So where here when I mention RYB, these are the rotor phases, not the stator RYB phases. So stator rotor three coils. If I plot the flux linkage versus time, the flux that is linking these coils with time, then the R phase coil flux linkage is sinusoid like this. Second phase is sinusoid, B phase is sinusoid as shown in the blue curve, and yellow phase as shown in the green curve. Now if this is the flux linkage, this is the flux linking, and what is the frequency? You can see one peak to another peak, that is roughly, that is actually 20 millisecond. So that corresponds to 50 hertz. So if we keep the rotor stationary and only give excitation in the stator, then when the rotor remains stationary, the magnetic field starts rotating. The stator magnetic field starts rotating. This magnetic field starts rotating. So at every instant, if we place some coils on the rotor, then there will be some rate of there will be some the flux linkages of those coils, and they will keep on changing, and we see from this plot, we'll understand later, that they are varying sinusoidally. They are varying sinusoidally with time. So we know this law, that induced EMF is basically d psi dt. Induced EMF is equal to rate of change of flux linkage of a coil. So if I plot only the R phase flux linkage, that is shown by this red one, you can see that it is directly same. It is same as the red curve on in the top side, in the top plot. uh, and if I take the differentiation of that flux linkage, and I get the induced EMF. So differentiation means it will lead that original flux linkage curve by 90 degrees. So that is what you can see, the induced EMF has shown. Induced EMF for this R phase coil, that is shown using blue color, and that is leading. So this is the flux linkage. The peak is leading the peak of the flux linkage curve by 90 degree. And we have the induced EMF, induced voltage across the R phase coil in the rotor, and similarly Y phase and B phase coils will also have some induced EMF across it, and they will also lead their corresponding flux linkages by 90 degree. That is clear. Now we'll understand, we'll go step by step. Okay, first we'll see what happens, or let us see here itself. I'll remove these portions, and we'll understand what we mean by flux linkage here. So you can see that initially at omega t equal to 0, so this is the axis of the magnetic field, right? So uh, if I go ahead a bit, I'll stop at this instant, some omega t equal to, so basically t equal to 4 millisecond. If I stop, then the magnetic field axis basically moves like this and becomes like this. So it cuts the R phase conductors directly, but because it is cutting, so you can see this is the surface, this is the surface of the R phase coil, half of the surface. So basically uh, the R phase axis is somewhere here. So in order to calculate the flux linkage of the R phase coil, we have to get the B distribution. So B theta, B along theta we have to get, and we have to take an integration from this point, that is the axis, one axis point, axis point, to the opposite, that is this point. So if it is some angle, say theta, then we have to take an integration of, so we know B theta. We have to take, in order to calculate the flux linkage, we have to take an integration of B theta from from theta to theta plus pi, right? So that will give the flux, and we have to basically this, what is this area? So flux is basically B dot ds. Here what is the area? Because it is a cylinder surface area or the side area of a cylinder, that is nothing but uh, pi uh, pi dl. So d is the diameter, is the surface area of um, of a cylinder. And if we take a, if this is a cylinder, if we take a small angle, say d theta, this is d theta at a radius r, then this one will become r into d theta. So this is the arc length, and the area will become r into d theta into L. So when we have to do B dot ds, this will basically come up to so the area is in the radial area vector, basically perpendicular to the circumferential thing, that is radial. So we have to take the radial component of B, and the dot sign will go out, because it is they are of the same in the same direction. So it will come out to be r into d theta into L. So you have to take the integration of that. R L, those will come out. So R L integration of B radial into d theta. So basically if I go back to any one of those B theta curves, yes, so we have some B theta curve like this. So suppose our rotor conductor at some given instant, there say one side is at 45 degree, another side will be at 180 degree ahead, that is 25 degree. So we have to take an integration in this region. We have to take an integration from 45 degree to 225 degree, and so the integration over B over theta for this region will give the flux linkage, or basically the flux, and that if we multiply by those factors, then we will get the, yeah, if we multiply by R and L, then we will get the flux. And if we multiply by the number of turns also, then we will get in terms of flux linkage. So at that instant, wherever I stopped earlier, at 4 millisecond, at 4 millisecond, it is, you can see at 4 millisecond, if I start from this blue point and end here, here in this left hand side portion, flux is basically moving radially out. So okay, so not here to here, we have to take from one coil to this point. I told it wrong. We have to take from there. When I explained, then I explained that we have to take from conductor position, conductor 1 to, basically turn 1 position to turn 2 position. I'll remove these things. So if our turn is here and here, then we have to take integration from this point to this point in order to calculate the flux that is linking this turn. Now you can see that in this upper portion, the flux lines are radially outward, say positive, although here they are radially inward, and that is perfectly symmetric. Basically at this instant, the axis of the magnetic field is on the conductor, on this turn. That means whatever positive flux this turn encloses, that is negated by the negative flux. So that means at this instant, 4 millisecond, the R phase coil has 0 flux linkage. That is what you can see here at 4 millisecond. the R phase coil has 0 flux linkage, and as it moves ahead, and when it reaches a position like this, where you can see that the axis the axis basically comes at the middle of the the surface that we are supposed to integrate over in order to calculate the flux. That means all over the place, all over this surface, the flux is positive everywhere or negative everywhere. So depending on the sign, it will be so at this instant it will be positive. If I again go ahead by some time, again we'll reach a point where again the axis of the magnetic field will be aligned to the two conductors, so the flux linking will be 0. Again if I move ahead, I will reach the exact opposite point, that is where the flux linkage is or maximum of the negative direction. So this is why if we have B distribution, some sinusoidal B distribution along the air gap, and if we uh, run the rotor, or that is B distribution that itself rotates, then if we have some stationary coils, then the flux linkage flux linking those coils will also be sinusoidal in nature. And one important question that you can ask is, the B distribution that we saw had so many harmonics, had so many notches and other things, but the flux linkage waveform seems so smooth. It is almost like a smooth sinusoid. How does it happen? So this can be answered like this. So the B theta that you have, that has some B1 sine theta plus B some harmonics, so Bn sine of n theta plus theta. Basically I should not write theta and this thing, so theta, some theta harmonic or whatever. Yeah, so sine plus cos you can assume like this, phi, basically phi n summation over Bn. So these are some harmonics. But when we are calculating flux linkage, then we are taking an integration over this B theta over theta. So integration, if this has some this is say B1 sine theta, then the integration will become B1 cos theta minus of that. If it is B say n sine n theta, then the integration will become minus Bn by n into cos of n theta. So you can see that the amplitude, because of integration, it gets divided by the harmonic order, that is n. That is why if we have reasonably high number of slots, that makes the slot harmonic orders to push in the higher orders like 11, 13, 19, 17, or of that order, then whatever is the small harmonic component amplitude, that will get divided by that harmonic order when we do integration, and that is why the amplitudes of the harmonics in flux linkages will become negligibly small, and that is why they will appear to be almost sinusoid, as you can see. If I move to this case, if I plot the flux linkages of this phase, then you can see that it is almost sinusoid, because of integration action, all those harmonic amplitudes are becoming negligibly small. That is why in flux linkages, although it is present in the B theta, in B distribution, radial component of B along theta, it does not show up in flux linkages that much. But induced EMF, it may show up, because again it is a differentiation. uh, yeah, but because flux linkage is reasonably smooth, so when you differentiate that thing, then they do not show up that much, so the induced EMF is also reasonably sinusoidal. So now let us see when so we will understand what happens to, so we have understood that if we excite the stator with three phase distributed sinusoidal currents, and if we keep the rotor stationary, then in that stationary condition itself there will be some induced EMF of the same frequency, that is 50 hertz of flux linkage is of 50 hertz frequency, and there will be some induced EMF of the 50 hertz. Now let us see what happens. Then we'll go to currents. First let us see what happens if the rotor is also rotating at, so the stator magnetic field is rotating at 3000 rpm in the anticlockwise direction. We have rotor conductors, we have some rotor turns, 3 turns. If the rotor, say something happens and the rotor starts rotating at 2400 rpm, let's see what happens to the flux linkages and induced EMF. Now this is what is found in the flux linkage waveform. You can see that I have plotted for 100 millisecond. I have plotted for 100 millisecond, and in 100 millisecond one cycle is getting finished, that is the frequency of the flux linkage of the rotor conductors is 10 hertz, right? That is 10 hertz of frequency that we can see. 10 hertz of flux linkage appear, or flux linkage waveform is some sinusoids with 10 hertz frequency. And same thing, if we get the induced EMF, if we differentiate the red color flux linkage waveform in order to get the blue color induced EMF, then again that will be of the same frequency, but it will be leading by 90 degree, and we have induced EMF of 10 hertz frequency. So what is this case? Here the stator magnetic field Fs that rotates at 3000 rpm in the anticlockwise direction. The rotor rotates at, this is our rotor, that rotates in the anticlockwise direction in 2400 rpm. So what is the relative velocity of the rotor conductors with respect to the stator magnetic field? That is 3000 minus
600.
yeah, that is 600 rpm, right? 3000 minus 2400, so 600 rpm if divided by 60, then this becomes 10 hertz. So we are seeing the same 10 hertz uh,
Rotating
sinusoidal
lamp.
flux linkage waveforms and 10 hertz induced EMFs in the rotor conductors, right? So we understand that if it is stationary, then we have 50 hertz of flux linkage and induced EMF in the rotor, and if it is rotating at 2400 rpm, then we have 10 hertz of flux linkage and induced EMF. So uh, we'll understand about the current, what comes. You can understand that there will be some current and there will be a torque production, and because when it is stationary, the stator magnetic field is rotating at 3000 rpm, the frequency of the rotor EMF and other EMF is also 50 hertz, so that will also rotate at 3000 rpm, so there will be continuous torque production. And say if it is running at 2400 rpm, then also there will be continuous torque production, because both magnetic fields will start rotating at the same speed because of uh, induced EMF, basically electromagnetic induction happening in the rotor coils. So that is all. So another quick thing, so if it is happening on its own, then do we need to actually put some conductor. So now what we are doing, we are putting some well-defined paths in the form of coils. So we are inserting some coil one side here, we are taking that and bringing it here. We are making distributed winding, similar to what we have done in stator. Now if we do not have to give any excitation to the rotor, can we not simplify it? Is it possible, is it actually necessary to plan the paths of the currents? If everything is happening automatically, can we not do something? So what is happening here is, if I try to plot it like this, so if this is R phase one side conductor, this is going and coming like this. So this is our one coil. Now if I go to the next one, uh, say this is the circle. Yeah, this is the circle, right? Now some other conductor may be here, some other conductor may be in this location, and like this they are going back, and they have some return path. And similarly we have B phase, uh, we have B phase conductor also. It will have some return path, and it will come back like this. So we have three coils wound like this. So we are having 2, 3, 4, 5, 6, these 6 terminals, and these 6 terminals here. If everything is happening automatically, then why to have all these things? We can simply short all these terminals together, and we can short all these terminals on this side together, right? We are leaving this end connections, we are just shorting. We have simple conductors, the two sides. For these we have 6 active conductors, that is 2 R phase, 2 Y phase, 2 B phase, 1 2 3 4 5 6. Those are there on a circle. So we are simply shorting all of that, right? We are simply shorting all these things together. So if I show the this view, then we have some ring like this. We have some ring like this, where say this is R phase one conductor, this is another conductor, this is blue phase one conductor, another conductor, and yellow phase one conductor, another conductor. All of these things are basically shorted by this ring. This is a conductive ring. So with this, all these conductors are shorted. This same thing is happening on both sides of this thing. So both sides we have a ring like this. We have these conductors, 6 conductors, which are basically short circuited. So we can even do this, and the same thing will happen. That we'll see what happens if we have this type of this is like a cage. So if we have a cage rotor, then what about the induced EMF in the bars, in these different bars? We'll look at that, and from there we'll try to understand the currents, because today for even the coiled case we did not look at the currents in different in the different phases. We just looked at the induced EMF. We'll look at the currents, and from there we'll understand the rotor magnetic field, and we will understand the direction of the rotor magnetic field, and we'll see that the rotor magnetic field is actually lagging behind the stator magnetic field for motoring case, and then we'll look at a generating case where we will understand how the rotor magnetic field is leading the stator magnetic field. Now if we look at those examples, then this confusion about stator magnetic field and rotor magnetic field, what is leading, what is lagging, that will go away as was there in the last class. So yeah, so is there any question now?
Yeah,
So
Samrat,
we
can you
have,
please go back?
yeah, just let me conclude. So we can either have windings on the rotor, we can excite the stator as well as the rotor, so that is called as doubly fed induction machine because we are exciting the stator as well as rotor. Or it is possible for us to make some cage and do away with giving any winding, giving any excitation to the rotor. Automatically some induction will take place, and rotating magnetic field of the rotor will get generated. So that is our squirrel cage motor, squirrel cage induction motor, that is with cage rotor. And another is wound rotor, where there is some winding that is wound, and we can give physical excitation to that, that is doubly fed induction machine. Yeah, which slide, sir?
Yeah, one slide back.
Okay,
Yeah,
44.
here, yeah. Here, why the induced EMF is seems less in amplitude when
Okay,
compared to the previous slide.
okay, so you can see, yeah, that is a interesting point I missed mentioning. So the flux linkage does not change with speed, right? Flux linkage, if the rotor position is like this, it will be maximum. So if the axis is like this perpendicular, then it will be maximum. And if the axis is along the winding, then it will be minimum, that is 0. That is very clear. So the flux linkage magnitude does not depend on speed, but actually the induced EMF depends on speed. Why? Because you have psi as some say psi maximum
Rate of
sine
change.
omega t, right? That is how that these are all sinusoids, so all these things can be safely represented by some sine omega t. If we take this as the 0 degree, this as our omega t equal to 0, if we take it like that, then this can be represented like this, the r phase flux linkages. Now what is r phase induced EMF? That is d psi r tt. What is that? Psi into psi m into this omega into cos of omega t, right? So when the omega, the frequency in this first case, when the rotor is stationary, then the flux linkage frequency is omega equal to 2 pi into 50 hertz, 50 radian per second. So this is the flux linkage frequency. But when we go to the next case, where the rotor is rotating at 2400 rpm, that means the flux linkage frequency reduces to f equal to 10 hertz. So in this case omega is only 2 pi into 10, this much radian per second. So it becomes omega, say omega 2, omega rotating, and omega, first one was omega 1, that is 2 pi into 50 radian per second. So omega 1 is omega 1 by omega 2 is equal to 5. Now you can look at the first case, induced EMF magnitude was this blue thing. If I go somewhere around 5 volt, in the vicinity of that. Now if I go ahead and look at this case, it will be somewhere around that, 1/5 of that. So earlier it was 5 volt I mentioned, right? Yes, around 5 volt. So it has become 1/5, approximately equal to 1 volt, because the frequency has reduced. So E equal to d psi dt. So the frequency gets scaled with the flux linkage amplitude to get the induced EMF amplitude. That is why. So if you recall, the induced EMF in the rotor, that is having a uh, this thing E into S2. So if S equal to 1, then that means at stationary condition, that is induced EMF is maximum. But if the rotor is rotating at high speed with slip reducing, then the induced EMF will also start getting reduce will start to reduce. And if the rotor rotates at exactly synchronous speed, now with respect to rotor there is no rate of change of flux linkage, so S equal to 0, so the induced EMF will also become equal to 0. Does it answer your
Yeah, I
question?
got it. Yeah, it's clear. So for synchronous machines, it will remain same for all the speeds, right? The amplitude, uh,
Yeah, that is why
the
in
flux
synchronous
linkage
machine
and
in
the
field winding, yes, in field winding there is no induced EMF.
mm, yeah.
In field winding you just give some DC excitation. There is
Yes.
no extra induced EMF in the field winding. Even if you
Okay.
look at, even if you measure this induced EMF, that will be exactly equal to whatever is the resistance multiplied by if some field current is getting injected. So the voltage across it, say Vf, will be exactly equal to if into Rf. Had it been not synchronous, then due to this field of the stator there will be some induced EMF in the field winding also. This
Okay.
equation would not hold. Yes. Any other question? If not, we'll close today.